Hi, we are Team MAST. My name is Leo.
I'm Jenny.
I'm Jack.
I'm Tommy.
And I'm Jin.
And we'll be talking about the device we created for the Duke Forest that will act as a resource for education and research by sorting mass from forest debris, such as leaves and twigs.
Masts are tree nuts such as acorns, beech nuts, and hickory nuts, and they play an integral role in the forest ecosystem as primary food sources.
Researchers at the Duke Forest want to research masts to understand various forest ecosystem patterns such as masting cycles and approach us with the desire for a more efficient way to collect and isolate masts.
Our prototype sorts tree mats or debris using their shape and kinetic energy. When slid down a ramp, the rounder mats will gain more momentum compared to irregularly shaped debris.
This allows mass to fly over the debris deposit hole, and the debris with less kinetic energy will fall into the gap.
The collection ramp is an 1/8-inch flat aluminum sheet fastened to the side walls. Its function is to direct mass into the sorting ramp. The sorting ramp is a curved 1/16-inch aluminum sheet bolted to the bottom of the base platform in the back wall. This ramp allows mass to gain kinetic energy while rolling down. The debris deposit hole is a gap of 8.5 inches away from the base of the sorting ramp, which allows debris to fall onto the forest floor. The collection box is in front of the debris deposit hole, made out of wire mesh and held together by a wooden rim built from pressurized wood. This stores and displays the mass for visitors. L brackets are attached to the box to allow it to slide along C channels for easy access for researchers. An acrylic viewing window in the front of the box allows visitors to see the mass sorting process. The side walls on the exterior of the device protect against weather and animals. They are made out of 1/2-inch pressurized wood. Lastly, the aluminum L brackets along the sides of the box are used to secure the walls and the ramps together.
In designing our final prototype, we used a Python model to simulate the behavior of mast and debris inside the device under ideal conditions. The model made use of potential and kinetic energy equations to calculate the trajectories of materials coming off the sorting ramp. This simulation was used to inform dimensions of the device and to calculate a plausible range of distances for the collection box.
When testing, we dropped 10 masts and 10 sticks from around 10 feet above the device in each trial of the 3 trials for each distance of the box from the ramp in the range chosen. The results from the test are shown in this graph, which shows the filtering accuracy in orange and collection accuracy in blue at each distance. These lines can be seen to overlap at around 8.5 inches, which represents the point where both filtering and collection accuracy are optimized. This supports the 8.5-inch separation shown in the prototype.
Overall, the accuracy design objectives were both met because 97% filtering accuracy and 100% collection accuracy were achieved at 8.5 inches during testing. In addition, we assumed that the device met the target value for low maintenance because none of the dropped mast or debris clogged the device. The device also met the target value for cost because the total cost of the device was $323.61, which is below the $500 budget.
Our final design prototype fulfills the design objective in terms of accuracy, maintenance, and cost, acting as an accurate and efficient resource for research and educational outreach.
For future steps, we have to conduct additional tests for durability and setup time. For the durability test, we will drop branches and splash water onto the device in order to simulate what would happen in the forest to see if it could last at least 1 season in the forest. As for setup time, we will time how long it will take for 2 people to set up and deploy the device into the forest. As for next semester, we plan to add additional components to sort by genus so that it could more efficiently help the researchers obtain mass for research resources. And finally, we hope to deploy our device in the Duke Forest after continuing these additional tests and adding these components to our device.
Finally, we would like to thank the following for their support throughout the engineering design and prototyping processes. Dr. Ann Satterback, Dr. Elizabeth Bugles, Murad Maximov, Megan Gendergeski, Tricia Dupnock, Jennifer Schneidig, and Sarah Childs.
Thank you for listening.